component, y component, and z component. So I gave it u, v, and then this is 2 minus v, which is exactly what we have. I let u vary between -1 and 1. I let v vary between 1 and 1 minus u, between 0 and 1 minus u squared. And then I tell it to plot it so that it's somewhat see-through. Okay, opacity 0.4 means that it's transparent. Opacity 1 means it's not transparent. Opacity 0 means you don't even see it. You just see the boundary of it. And then make it red. And then I tell it about how to draw the axes and things like that and how to label them. But
you said this is based off C++, right?
it is, but it's C++ basic language here. But imagine just a bunch of built-in functions. When I first started coding in Mathematica, a lot of it was like more C. You had to code. Now there's so many built-in functions, you know, that you just, all I do is bring up this thing called a palette, and I can call on all these different functions. Like if you want to do, man, there's pretty much anything is here. If you want to integrate, where's the algebra one? Simplify, expand, factor, it goes on. So really, I'm not coding as much as I understand the syntax, but a lot of it is just pulling on other subroutines. All right, well, we're left with one more, right? S3. So for S3, the difference between S3 and S4 and S2 is that it's just the edge, right? Just the edge. So I don't have to fill the inside. And that's good. That should free up a variable. And I can use that other variable to control the back and forth. So what do you think? You help me out here. S3. Draw me the boundary without any care at all right now about the y coordinate, back and forth. Draw me the boundary. How are you going to draw me the boundary? X is u, and what's that? Z is v. Look. You want to draw, look, this is it, right? This is the xz plane. So I'm looking at that from here. I'm trying to draw just the blue. The blue is going to lie on here, right? But not the inside. So it's got to follow this equation right there. 1 minus u squared, because u is our x. You see that? You see that's a big difference here. Because here our v, we varied it between 0 and this, which drew everything in between. When I don't use v here and I fix it, it's just going to draw that edge. We need that because we need the v for this part, for the back and forth. So now I'm fixing a point on this edge. Once I fix a point, I need to vary back and forth between here and here. And that's between where and where? Y equals 0 and 2 minus z, right? Which for us is something else, right? So what do I call this? V. Let this be the thing that you're going to control down here. U's between where and where? -1 to 1. V must be between 0 and this plane, which is 2 minus z, but z for us is this. So 2 minus 1 minus u squared, which is really 2, not 2, which is really 1 plus u squared. Understand that? So?
Yeah, I got it.
I'm going to draw 1 point for you. You give me a, let's take a test point. If I let u be 0 right now, right? If u is 0, then I'm right here on the, it's like x being 0, right? What's my z coordinate going to be? If u is 0, what's my z? 1. So I'm 0. I go up to 1 on my z. Now, what is my y coordinate going to do? It's going to be v, and v is going to be between 0 and 1 plus u squared. But what was u? It was 0, so it's going to be between 0 and 1. 0 and 1. There we go. It's going to draw me all those points. Okay? Let's do another one. What if u is 1? Where am I going to be? If u is 1, I'll go out 1. What's my z? 0, so I'm here. And then I'm going to let my y be between, my v, which is my y, goes between 0 and 1 plus 1 squared is 2. So 0 all the way out to 2 gives me that. Does that make sense what's happening here? I'll take one more just for fun. If I take 1/2, that's here. 1/2 right here, I go up what? 3/4, which is there. And then 0 to what, 1/2? 1 plus 1/4, right? Which is this, which is further than this one, right? That one was 1, this one's 1 1/4. All the way down here was 2. Understand? All right, that is the essentials for parametric surfaces. We will need this not so much in this section as much as we will in the next section. All right, 13.7. Oh, there was one more thing I wanted to show you. It's related to this, but it's not in the notes. Everybody knows the equation of a plane, right? Equation of a plane. A, x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, c is a normal vector and x naught, y naught, z naught is any point on the plane, right? We're all familiar with this. Okay, we have another way that you can come up with the equation of the plane. This is the vector form of equation of plane. Now, recall this formula. Remember that? That was the vector equation of a what? Line. This is a line, right? And what happened basically is that we said, give me a point on the line, and give me a direction vector, and then give me all scalar multiples of that direction vector, and I'll draw every vector in that direction and in this direction, and it'll create the entire line. Right? Basically, that's it in a nutshell. We're going to now do the same thing for a plane, but here's the difference. Plane is going to have, a line just really have one direction. For a plane, we're going to need two directions. So somebody give me a point, right? Start with a point. Give me a direction vector, not the normal vector. Give me a direction vector. This vector needs to live on the plane. So let's use this wall as an example of a plane. I pick a point on it, take a vector on that plane, take another vector on that plane, like this. If I take every multiple of this vector and just don't even care about this, it'll draw this line, won't it? Now, what if I add this vector to every one of those? Then I'll have another line that's parallel to this, won't I? Oops, like that. What if I take this, every one of these vectors on parallel to this line, and I add half of this one? I'll have another line going in each direction like that. And if I do that for every multiple of this line, then I'm going to create the entire plane, aren't I? But you could also do it by saying, take this vector and this vector, add them together, parallelogram rule, you'll get this vector. And then you do two of these vectors. Parallelogram rule, you'll get that vector. Do three of these, parallelogram rule. Do every multiple of this with every multiple of this, and you get the whole plane. All right? So what our equation turns out to be for the vector equation of a plane, it's going to still require a base point. I'm going to use u and v because it's a surface, right? So it's got to have u and v in it. I start with the base point, base vector point. I add to it every multiple of some direction vector. So I'm going to say u times the vector, I'm just going to make it up, a, plus v times the vector b. Do you all see that this is the same formula as this? Take this out, and this is r naught plus the t is now u, and the v is now a. But now I'm adding a separate vector, a different vector, and all the multiples of it. So what we're doing is we're taking every linear combination of these two vectors, which is called the span of those two vectors, which in this case would be a plane. As long as these vectors are not parallel. If they're parallel, then you won't get a plane. You'll get a line. But okay? I just want you to be familiar with that, just like you've seen it before. All right? There is a way to draw a plane with two vectors. It just requires two vectors on the plane. Now we can get into 13.6. 13.6, yes. Parametric surfaces and their areas. All right, what we just learned a minute ago in the last class, ignore that please, is that if we have a vector function r of u v, that this will draw us a surface in three-dimensional space, right? That's what we took time practicing, trying to come up with the formulas for these surfaces. One example of a parametric surface that you don't quite remember as being a parametric surface was when we did spherical coordinates. Do you remember when we did spherical coordinates? We switched over, we let x equal rho, sine, theta, cosine, phi, all that junk. We had three variables, didn't we? Rho, theta, and phi. If we fix rho, right, if we fix rho, that was the radius of the sphere, then we only have two variables. So look at this example right here. If I take my r of u v to be sine u cosine v, sine u sine v, cosine u, then, hold on a second. Ooh, yeah, the u is like the phi, just so everyone knows here. The u is like the phi was, and the v is like the theta was when we use polar. Okay? Then if I look at, where's my picture? There it is. if I, where is it? Hold constant. I want to hold the v constant. So if I hold my v as a constant and let my u change, I'm going to draw these little semicircles. If I hold my u constant and let my v change, I'm going to get all these circles in the other direction. And if I put all these together, I get all these grid lines together, and it creates the sphere. All right? So now let's talk about derivatives. If you have a vector function, back when we were drawing curves, then the derivative of that vector function was a vector that was tangent, right? Tangent to the curve. As a reminder, it looked like this. Here's a curve, and then we move this thing around. That red vector there was r prime of t. And we know that we could extend that line, or the vector, out in each direction and create a line from it, right? Now, what does it mean to talk about the derivative of our vector function of two variables? Well, if we have two variables, then we can't take a derivative unless we hold one of them constant, like a partial derivative. So if you see this r subscript u, what it means is take the derivative of the vector function, treating your v like a constant. If you see r sub v, you take the derivative holding u as constant. But what does it mean geometrically? So here it is. If you hold, here's a point, right? If you hold one variable constant, you're going to get a derivative, and that's going to give you a vector, which would be something like this. If you hold the other variable constant, you get a different vector, which would be the one like this. Each one of those is tangent to the curves respectively, right? So this one right here is tangent to the green curve. This one right here is tangent to the red curve, right? Would you agree that both of those together, both those vectors together, live in a plane that is tangent to the surface? Yes? All right. And that's exactly what we have in this picture. So somehow the derivative, with the derivatives of these vector functions, we can come up with tangent planes to surfaces using this. This picture is just supposed to make you believe that that plane is tangent to that sphere. All right, so here's the first problem that we're going to do. Let's find the equation. Find the equation of the plane that is tangent to the unit sphere at this point. Any ideas? What's your idea?
Use that vector sine u cosine v.
Okay, so let's first let's draw the surface, right? We got to be able to draw the surface before we can find a tangent plane to it. How do we draw this surface? R of uv will be equal to, how did I have it written there? I think it was sine, I think I did sine, yeah, I just switched the order on accident there. Tell me if this is what I had up there on the previous note. Cosine u. Is that what I had? Oh, those were both supposed to be different. I don't know why I didn't write that one. Okay, and the u was our phi, right? Between 0 and pi.